So we've been talking about atoms, and then we got into electrons, and really the idea of electrons as a transition, as we've talked about, from one energy level to the next. That's going to require a certain amount of energy to do so. Again, if we have an electron on a lower state of energy, it needs to absorb energy, the atom, and that would be an endothermic process at that point. Much like what you did with the flame or the lamp the other day, it's going to gain energy. It's going to excite, again, those electrons to a higher state of energy. And eventually, as we've been talking about, they really do want to sort of relax back down to a lower state of energy. And that process will occur. And again, it's this sort of conservation of energy. In order for it to come down in energy, the atom will have to release that to allow the electrons to really transition back down. Again, the electrons can be released, that energy, in the form of a wave, which is sometimes referred to as a photon of light, which may have a specific wavelength. That obviously would be an exothermic type process when the atom releases that energy. And what we can see is what is sometimes referred to as an emission spectrum. So the emission spectrum is when those electrons, again, are sort of dropping energy levels, releasing that energy to the surroundings. And again, as we saw with both the sort of the flame test and the light the other day, if it falls in that visible part of the spectrum, we will see color, right? We'll see our red, orange, yellow, green, blue, indigo, violet. A reminder as well that not all electron transitions will result in a visible sort of spectrum being released there in terms of the wavelength. So it is possible to release a wavelength that falls outside of the visible spectrum, like maybe one of those questions, yes, that she might have answered. Now, when we talked about waves, there are some functions or properties of waves that are important. We obviously have our wavelength here. We also have our frequency for the wave. Frequency is the new symbol there, and it typically has units of reciprocal seconds or hertz, and those are basically a one-to-one conversion between them. We could take the speed of light is equal to the wavelength times the frequency. Obviously, the speed of light being a constant of 3 times 10 to the 8 meters per second. Our frequency being reciprocal seconds, and the wavelength here does need to be in meters, so that we end up with the meters per second sort of relationship here. So if you know the frequency, you can figure out the wavelength. If you know the wavelength, you can figure out the frequency of light. We also talked about the idea that the wavelength and sort of the frequency is related to energy. The longer the wavelength, very badly drawn there, but the longer the wavelength there, sort of the lower the frequency, and that usually is a lower energy type of wave, as opposed to a much smaller wavelength. So a smaller wavelength usually will have a much higher frequency, and that usually results in higher energy that occurs. So as these electrons, again, are sort of transitioning, they're giving off this energy. And again, it can fall really anywhere in that electromagnetic spectrum that we talked about and saw the other day. Again, we have things like radio waves and microwaves kind of on the short, the longer wavelength, lower of energy. Then we kind of progress up through that. We have some infrared, some visible part, again, is where we see colors, some UV, a little X-rays, some gamma rays, which are more on the shorter wavelength, much higher in energy sort of area of the electromagnetic spectrum. You could actually calculate the energy associated with a photon of light by taking E is equal to H times the frequency. H is Planck's constant, and that is 6.63 times 10 to the minus 34 joules times second. Joules is a unit of energy, and obviously seconds is time in that case. So because we also know, and we saw earlier, that the wavelength is times the frequency equals C, we could solve for frequency, which would be C divided by wavelength. which means we could substitute that in there and also use this version of the equation where both of these are obviously constants. That means that if you also just know the wavelength in this case, you can figure out the energy associated with that wave by basically plugging it in there. The wavelength, obviously, in that case, in this calculation would need to be in meters so that everything, again, does cancel out correctly. Any questions on that there? We also touched upon the idea of how elements, like what we looked at the other day, how they sort of gain and lose energy. And it's this sort of quantized version of energy where they either gain a quanta or lose a quanta of energy. And that is basically displayed by sort of that equation. Remember, this idea of gaining and losing energy in this sort of quantized fashion is again equivalent to sort of like the stair example. Much like that, electrons will gain or lose enough energy to really fully transition from one energy level to the next. Just like when you walk on the stairs, you're pretty much on one step or the other. You usually don't rest like halfway between the steps, and it's sort of the same idea there. They will fully transition from however many energy levels they're going. They won't really stop in the middle or anything like that. And that's different than a continuous sort of spectrum. And in a continuous spectrum, it's oftentimes sort of explained like walking up a ramp. And obviously, if you walk up a ramp, you literally can stop anywhere along the way. You pretty much can hit every part of that. And that's sort of the same idea. So it's things like the sun, again, will sort of give off more of a continuous spectrum. You know, you got light, you got heat, you got everything sort of coming off at once. But the elements will give off more of this quantized sort of version. The result of that is much like what we saw in the experiment there. You will end up with a nice, pretty lines, because each of those lines basically is a result of those specific energy transitions that occur as electrons move from one energy level to the next. And again, that's pretty much what we see there with elements. Each element has its own unique line spectrum based on the colors that you see, the wavelengths that they break out. Any questions on any of that stuff we talked about last time there? Yeah. So this is sort of the four major lines that you sort of see in the hydrogen atom. And again, you see these distinct lines. Remember as well, these color lines also sort of represent energy as well. As we know, right, this is a longer wavelength than this, which means this is a little lower in energy than, say, this guy, right? So if we see this red line that pops up, this is a result of probably a transition that isn't involving a lot of energy levels, right? Because it's only going to take a little bit of energy to do so. That's different than, say, what we see over there in sort of the purple region. That's a much shorter wavelength, which is much higher. So that may be an actual transition of an electron from multiple energy levels coming down, which would result in more energy that you see. So the significance of this idea of energy is that only certain energies are allowed for an electron in the hydrogen atom. So the idea here is obviously hydrogen atom is quantized, which again is why we see those distinct lines coming off. Otherwise, if it was continuous, you would pretty much see like a nice rainbow. Everybody would be coming off, you know, kind of all at once. All right. So and that's sort of what we see with the white light. So that brings us to really a model of the atom to sort of explain these lines that we see in the hydrogen model. And this is the Bohr theory of the hydrogen atom. And the Bohr theory of the hydrogen atom is not correct in all aspects of it. But it does sort of very nicely explain sort of what happens with hydrogen and the four lines that we sort of see with hydrogen. But when we do get multiple sort of electrons happening in an atom, it doesn't really hold up. So it's also what is sometimes referred to as sort of like the planetary sort of model, where we have the nucleus and we have these electrons that are in these orbits. and like n equals 1, n equals 2, n equals 3. And the idea behind sort of Bohr's model is that these electrons are moving around these nice, pretty sort of orbits. And if an electron, was happened to be out here in this orbit and it transitions down, say, to there, it obviously would give off a wavelength of light at a specific wavelength that would correspond to one of those colors that we see. Again, the electron is restricted to either being in that orbit, right? Or it has to be in another orbit. It won't, again, find itself in between orbits or anything like that. Again, this idea of quantized energy, it's either going to have enough energy go fully to one, or it will have enough energy to gain to fully transfer to another. When we talk about energy levels, n is the actual, what is known as the principal quantum number. And again, that's sort of a fancy word for energy levels. And as we'll talk a little bit more about in a bit here, n equals 1 is the ground state. That is the lowest in energy. That is sort of the closest to the nucleus. Anything above that, like n equals 2 through 7, again, these are what are referred to sometimes as excited states. So these are higher in energy, a little further away from the nucleus, and as electrons sort of transition. As we'll talk about, again, works nicely to sort of explain what we see with hydrogen. Doesn't really hold up past that. And as we will later talk about here, electrons really don't move in pretty circles around an orbit where you could just kind of put your finger up and wait for it to come back around the turn. They don't move like that around the nucleus or anything like that. They actually move really randomly about the nucleus. So this model is definitely not correct in all aspects. It's a model or a theory, as we talked about at the beginning of class, something that obviously can be revised and rethought of. So as we look at this here, we could see that maybe some of the reasons we see those lines in the hydrogen atom is these transitions. So when we look at that red line, like we were talking about a second ago, perhaps it's a transition from the third energy level to the second, which is really just one energy level transition. As you can see here, not very big. But maybe when we see more of that blue line, it's going from the fifth energy level to the second, which is several energy levels. It's going to kind of go past there to get down there, which is going to require a lot more energy to be released. And thus, we see a much shorter wavelength of light coming off in that photon. Remember as well, another idea that we talked about is the idea that things like photons have both particle-like function and also wave-like function. So it's sort of that dual nature of light that occurs. So here again is those transitions. You can see that blue line making a lot more energy transitions than say the red one. And again, that accounts for the difference in energy that we would calculate for that. And also the wavelength that we would expect. Again, we would expect a much longer wavelength there in the red area than the guy that's transitioning multiple energy levels down the road. So for a single electron, we could actually calculate the energy associated with the transition from one energy level to the next, like we did in that lab. And we pass around the sign-in sheet, print your name legible so I can read it. So this is the equation that we saw. This is the change in the energy is equal to minus, and again, you can use a rounded number here, 2.18 times 10 to the minus 18 joules. This again is what is sometimes referred to as Rydberg's constant, RH. And this is 1 over n squared final minus 1 over n squared initial. This is your final energy level of the electron where it ends up. And it is the initial level of where it started. And this change of energy is the same equation that you could substitute in here as well, which is our h times our frequency and also our hc over our wavelength. So if you have an electron transitioning, you could use this equation here to calculate the energy associated with that. And you could also obviously figure out the frequency of light that's going to be associated with the wavelength that's going to come off of that, and also the wavelength that would be for that photon that would be released in this case. A couple of things that we talked about during lab and also that you should remember here. When you calculate the change in energy or you calculate energy in general, Again, you should leave either the positive or the negative sort of sign on that, as that would indicate whether it's endothermic or exothermic type of process that's occurring. You do need to sort of get rid of the negative sign if you have one for energy, when you go to take it on and continue the calculation for something like frequency or wavelength. Those things do need to be positive numbers. So again, you shouldn't have like a negative wavelength or a negative frequency when you do that. There are some different versions of this equation, but we will go with this one here. So Bohr's model, as we mentioned, sort of correctly fits the quantized energy that we do see in hydrogen. An electron is really sort of bound to the nucleus, and that is because obviously the nucleus is overall positively charged, right? Electrons are negatively charged. So there is going to be some attraction, obviously, between the electron that's orbiting the nucleus and that nucleus, which is positively charged. So as an electron is brought closer to the nucleus, again, energy is released from the system. And as we talked about, there is what is referred to as sort of an absorption spectrum or an absorption process that's happening, and that would be when the electron goes from a lower energy state to a higher energy state, right? It's got to absorb energy. So the atom again would be positive in terms of the energy being absorbed. And as we've been talking about, mostly as it transitions from a higher energy level to a lower energy level, again, the atom is going to be basically negative or exothermic as it releases it. So Bohr's model, as I mentioned, was found obviously to be incorrect. The model works really well for hydrogen, but does sort of fall apart once you get multiple electrons sort of involved, as there is electron-electron repulsion type things that occur. So these things are really different. Electrons, as we know and as we'll talk about, really do not move around in circular orbits. You basically have the nucleus, and in that empty space, you have electrons really moving around pretty randomly about that empty space. There's really kind of no sort of pattern like it would be in an orbit, where again, you could just wait for it to come around the turn or anything like that. It is moving randomly. And as we'll talk about, that Heisenberg uncertainty principle basically states that again, as you know more about how it's moving, you know less about where its location is. So we will move away from this idea of orbits to ones that you may be familiar with, which are orbitals, of where we sort of find electrons in the atom in a more quantum mechanical sort of definition. So why don't we do some calculations here just to make sure, again, that we understand how to do it. What color of light is going to happen for each of these? Why don't we calculate the change in energy for each of these transitions? Let's also calculate the wavelength in nanometers. And let's also calculate the frequency for each of these transitions. So take some time here, work out each of those things for these three transitions. Once again, our friend nano is 10 to the minus. Okay, let's take a look and see how we're doing. So we'll start with the first transition here, which is something. We'll go n equals, I think, 5 to 2, I think. So we'll start with our equation there. Our change in energy is equal to minus 2.18 times 10 to the minus 18, which is our Rydberg constant, 1 over our final energy level minus 1 over our initial energy level. So putting in here minus 2.18 times 10 to the minus 18 joules, that's going to give me basically 1 over my final, which would be 2 squared, right, which is 4, minus 1 over 5 squared, which is 25. So cleaning up what's inside there, parentheses first, and then multiplying, we will get an energy of about 4.58 times 10 to the minus 19. The units here would be joules, which would be our energy. Any questions with that? So, at this point, we do have the energy. So we can use our E is equal to H times the frequency. By the way, this would be negative. Since I forgot my negative there, put the negative in there would be good. So here we're going to take E is equal to H times the frequency. We're going to solve for the frequency here, which is going to be E divided by H. And that is going to give us our E, which again, as we talked about, now that I included it in there, which I should have, we do want to get rid of the negative here on this part of the calculation. So that's going to be 4.58 times 10 to the minus 19 joules divided by our Planck's constant, 6.63 times 10 to the minus 34 joule times seconds. Here, the joules will cancel out, and that will leave you with reciprocal seconds, which is what we want for a frequency. So we'll take that number there. We'll divide it by 6.63 to the negative 34. Remember, you definitely want to be using your exponent button on these calculations. 6.91 times 10 to the 14. Reciprocal seconds would be our frequency. At this point that we have our frequency, we can go, our C is equal to the wavelength times the frequency here. And solving for our wavelength will be C divided by the frequency. That will get us our 3 times 10 to the 8 meters per second divided by our frequency of 6.91 times 10 to the 14 reciprocal seconds. Here, the seconds will cancel out, and that will leave us meters as our number there. And 3 exponent button 8 divided by 6.91 exponent button 14. And it helps to punch it in right. So let me try that again on my calculator here. No negative on that 14. There we go. So that is going to give us, we got 4.34 times 10 to the minus 7 meters. Here we are looking for nanometers. So a reminder again, in 1 nanometer, there are 10 to the minus 9 meters. So again, that is the correct way to use that conversion. So we got 4.34 times 10 to the minus 7 meters. 10 to the minus 9 meters on the bottom, which is really 1 times 10 to the minus 9. And we will take that and divide it out. And that'll give us 434 nanometers in this case. And that's somewhere probably in the blue range of color on the visible spectrum. Yeah. Any questions on any of this? Yeah. We do. So again, although I dropped it before I meant to, you do want to include it there with the energy calculation, which is again why I kind of squeezed it back in there. But you do want to drop it when you continue on to do any type of frequency or wavelength calculation that uses it. Again, you should not really ever end up with a negative wavelength or frequency, but you definitely can end up with a negative change in energy or value. Question? Why is it? I'm sorry. Because it is the energy level squared. So basically it's 1 over 2 squared minus 1 over 5 squared. Yeah. Yeah, so that one, remember, this is a different equation than the one that was in the lab manual. The one in the lab manual was about the acceptable energy level for an electron on a particular energy level, not transitioning. This is one where the electron is actually transitioning. So this is the equation that we talked about in the lab as well, that you want to use when the electron is transitioning from one energy level to the next. If you just want to know what the acceptable sort of energy of an electron, say on the 5th energy level, then you would use that other equation that you're talking about, which is the z squared over the n squared. But this is for the electron that's actually transitioning. Other questions? All right, then let's take a look at the next one here, which is we're going from n equals 4 to n equals 2 in this case. So we'll start with our same calculation here for our change in energy, minus 2.18 times 10 to the minus 18 joules. Once again, this is going to be our final, which will be again 1 over 2 squared minus 1 over 4 squared in this case. And that will obviously give us 1 over 4 and 1 over 16. So we'll do that there. And we'll times it by 2.18 to the minus 18. Again, making sure to use our exponent button. And this time I will not forget the negative. So negative 4.09 times 10 to the minus 19, right? So that is the energy basically being released, right, by the atom. It does make sense, right, because our electron is starting at a higher energy level, right, and ending at a lower energy level. So we would expect the change in energy to be negative or exothermic. If the electron was going the other way, started at the second energy level and ended at the fourth energy level, what's the only thing that would change? Yeah, it'd be positive, be the exact same number in this particular case, but it would be positive because it's going to be endothermic. So again, that also demonstrates what we've talked about. You know, there's a sort of perfect exchange of energy, right? So if it takes that much energy for it to go up that many units, it's going to have to release that much energy to come back down the same amount of energy levels. At this point, we can, if you wanted to go shoot at wavelength first rather than frequency, you could use E is equal to HC over the wavelength, right? And we have all that information. That would mean that the wavelength is equal to HC over E. So if we took this root of the calculation, which is perfectly fine to do, these are our two constants. So our 6.63 times 10 to the minus 34 joules times seconds, and our 3 times 10 to the 8 meters per second, divided by, again, here we are going to ditch the negative sign here, so we do not get a, and that is joules. We do not get a negative value for our wavelength. Here, the seconds will cancel. The joules will cancel. That will leave us meters as our unit here. So 6.63 to the minus 34 times 3 to the 8 divided by 4.09 to the minus 19. That's going to give us 4.8, we'll call it 6 times 10 to the minus 7 meters. Once again, we'll do our conversion to nanometers in this case. So again, 10 to the minus 9 meters and 1 nanometer. And that will get us 486 nanometers. And that's somewhere in the greenish range, I think. And at this point, we now have the wavelength, and we also have the energy. So you really have two options as to how you want to get the frequency. You could use the equals h times the frequency. You could use the c is equal to the wavelength times the frequency, since we also now have the wavelength. If we went with the c is equal to the wavelength times the frequency would be c divided by the wavelength. The important part here is units. We want to be careful, because if we do it this way here, that is meters, which means we do need to use the meters version of our wavelength, not the nanometers. Otherwise, we'll be off. So that would be 4.86 times 10 to the minus 7 meters. That way they cancel out correctly. And we will end up with 617, it looks like, to the 14. 6.17 times 10 to the 14. Once again, this is going to be reciprocal seconds or hertz as our frequency here. Any questions on any of those steps there? Then let's take a look at the last transition here in this problem, which is 3 to 2, it looks like. So we're going from n equals 3 to n equals 2. So I might as well again start off with our energy. Just really kind of the only thing you can start off with in this problem. We're going to do 1 over 2 squared minus 1 over 3 squared. So that's going to give us basically 1 over 4 minus 1 over 9. And then we'll times it by our 2.18 to the minus 18. And that's going to give us a 3.03 times 10 to the minus 19 joules. And again, this is going to be negative as our electron is transitioning from a higher energy level to a lower. I'm going to go with the E is equal to H times the frequency here to solve for the frequency. So the frequency will be E divided by H as I bring this to the other side and divide. That gives me 3.03 times 10 to the minus 19, getting rid of the negative sign, divided by our 6.63 times 10 to the minus 34 joules times seconds. Once again, the joules will cancel out, leaving us with 1 over seconds. And we will end up with 4.57 times 10 to the 14 reciprocal seconds. And again, here at the end, you do have a couple of options. We do have the frequency, we do have the energy, so you can use either one of these to get to the wavelength. And they both, again, should get you there in the same spot. So we'll do, I'll go with this one here. So wavelength going to be C divided by our frequency. Going to be 3 times 10 to the 8 meters per second. 4.57 times 10 to the 14 reciprocal seconds. Seconds are going to cancel. That will get me 6.56 times 10 to the minus 7 meters. And doing our conversion there to convert it into nanometers in this case, since we're looking for visible light, which is typically given in nanometers. We'll do our 10 to the minus 9 conversion there. That's going to give us 656 nanometers in this case. And I don't know, orangey, red, yes, orange, red. In terms of color. Any questions on how to calculate any of these things? You should be professionals. So what's Al's answer? I guess really what the question asked, which I think was the longest wavelength, if I'm not mistaken. Is that what it was asking? So if it was asking for the longest wavelength here, we have this last transition, which is 656. We have the one before it, which is 486. And we have 434. So obviously the shortest wavelength, right, is our blue one here. Now our shortest wavelength should also have the lowest or highest energy. Should have the highest. So it has 4.58 times 10 to the minus 19 versus our lower energy one is 303, right? So it has the higher energy that we would expect. And we also can see transition-wise here, our longer wavelength, lower energy is a 3 to 2 transition, like one energy level, while our kind of higher energy, smaller wavelength is a 5 to 2 transition, multiple energy levels requiring more energy to do so. Any questions on how to do any of those calculations? Do they agree? That's good. All right. So let's talk about some other behaviors of waves and electrons. And another important sort of idea, and it does fall back to this kind of dual nature that we've been talking about of waves having particle-like functions and particles like electrons having wave-like functions. This is de Broglie. And de Broglie proposed that particles could have a wave-like character, and that wavelength of a particle is inversely proportional to its momentum. Because it's so small, the wave character of electrons is significant. He actually didn't do any experiments. It was just all sort of he thought it up, sort of. And actually later experiments were done to sort of prove that it was correct. The idea of this is sort of the idea of like a standing wave. You know, when you pluck like a guitar string, right, and you have like a standing wave, right, you see it moving through space, but it's attached sort of to the guitar. It's not going to go anywhere in that sense. So we think about sort of electrons as well, you know, kind of a similar sort of idea as we move away from this orbit sort of idea. We think of them as obviously attached to the nucleus or attracted to the nucleus because of the positive charge, and they're negatively charged. So that's sort of the point of attachment, but they are kind of moving through space in this wave-like function, even a particle like that. So we could calculate what is sometimes referred to as the de Broglie wavelength. And that is this one here. That is the wavelength is equal to h, which is our Planck's constant of 6.63 times 10 to the minus 34 joules times second. I think maybe the S got left off your notes or not, but there should be another seconds hanging out there. Divided by the mass in kilograms times the velocity in meters per second. So the relationship here is between joules, and that the idea a joule is a kilogram meter squared second squared. So that is another sort of definition of a joule, which is a unit of energy. The nice thing about it is it's still Planck's constant. So even though you kind of put that in here, so this joule right here is what that is right there. So even though you sort of can change the units to that kilograms meter squared second squared, the number doesn't change. So it's still the 6.63 times 10 to the minus 34 number. What it does affect is really two parts of this calculation. It affects the mass. The mass of your particle has to be in kilograms and not grams, so that everything properly cancels out. So when you calculate the de Broglie wavelength, it does need to be in kilograms so that it will properly cancel out with the guy on top. And the velocity, whatever unit of velocity it may be, if it's in miles per hour or something like that, you need to get it into meters per second so that it will also correctly cancel out. So when you do that, if we just look at the units on the right hand side for the joules, we will have kilograms meter squared second squared, and we'll have another second that is there. That would be divided by kilograms times meters per second. So how everything cancels out is kilograms on the bottom cancel kilograms on top. 1 second here and 1 second here cancels out both of the seconds there. 1 meter cancels out 1 meter there. And the only thing left is a meter, which is the unit of wavelength that we end up with. So the two things you got to watch out for in these type of problems, if you're calculating the Broglie wavelength, is you do need to get that mass into kilograms, and the velocity does need to be in meters per second for everything to properly cancel out correctly. Any questions on that? So let's take a look at one here that calculating a de Broglie wavelength. Why don't you give it a try? Calculate the wavelength of an electron that is traveling at 2.65 times 10 to the 6 meters per second. The mass of an electron, 9.11 times 10 to the minus. Okay, so if we do this calculation, our wavelength is equal to h times our mass times our velocity in this case. In this particular problem, everything is nicely in all the right units and won't always be. So you might have to do some conversions, obviously, as you do this. So our h would be 6.63 times 10 to the minus 34 joules times seconds, divided by our mass, which in this case is in kilograms. And again, if it wasn't, you might need to do a conversion. And our velocity here is also in meters per second, which is really nice. So it's in the right units as well. Once again, this joule right here does represent a kilogram meter squared second squared times seconds, divided by our rest of our numbers here. Thus, our, once again, kilograms will cancel, seconds will cancel, and only one of the meters will cancel, leaving us in meters at this point. As you can see, even though we changed the units, h is still the same value, so that's not a big issue, hopefully. And we will end up with here a wavelength of 2.75 times 10 to the minus 10 meters, I believe, in this particular case. So we could calculate the wavelength of a particle like an electron, right? And again, this is that dual nature of sort of light. Although it is a particle, right? We could have a stream of particles that move like a wave, and thus it has a wavelength sort of characteristic to it as well. Just like, again, waves can move like a bunch of particles together, so they have particle-like function that happens as well. Any questions on that calculation? So what we are seeing is, as we sort of try to move away from the Bohr model of this nice planetary model where electrons are in these orbits and circling around the nucleus, to this more quantum mechanical sort of model of the atom, where we really don't know at any given point where we can find an electron, and really its location. As I mentioned a couple of times up to this, that is basically what is known as the Heisenberg uncertainty principle. That's its uncertainty in its position here, basically its position. That is basically how it's moving, and it's greater than or less than there are Planck's constant times 4 times pi. We're not going to do any type of calculation, obviously, with this formula, but the idea behind it is what we've been talking about. We're not going to have our electrons for sure. I know it's just going to be circling around, so I know how it's moving. I know exactly, if I put my finger here, eventually it'll come back around, like Bohr's model suggests. To this idea, again, of really what this says is, again, the more you know about one thing, its position or how it's moving, really the less you know about the other. So when we think about electrons, again, really random sort of movement around that empty space and around the nucleus. As we'll talk about here in a second, the best that we could do is there's a high probability of finding an electron in a particular location in atoms. So we move away from this kind of certainty of it moving around in circles to this idea of, I'm not really sure where it is at any particular point in time, I'm not sure exactly how it's moving, but what I do know is in this part of the atom, there's a fairly good shot that at some point you will find an electron here. As you move away from the nucleus, there's a good shot that you might not find an electron there. And that is what is sometimes referred to as wave function. And there's a guy named Schrodinger, and he has a bunch of nice, fun calculus type of derivative equations that if you ever take physical chemistry, that's like the first part of it. But basically a lot of what his calculations are really the basis of when we think about orbitals, and really what orbitals are probability maps. Again, theoretical locations within an atom as to where you would have a high probability of finding an electron located. Are there really any sort of orbitals, as we'll see, that are like, figure eights and those other weird shapes that they are? Probably not, but they are sort of mathematical explanations and probability maps of where you can find it. So when we talk about probability, and if you see a probability map like we might take a look at here in a second, usually any type of darker the color is a much higher probability of finding, for example, like an electron, and sort of the lighter color is a less of a probability of finding an electron. And what we usually see in terms of the color is, near the nucleus, probably pretty dark. And again, as you sort of fan out from the nucleus, there's going to be less of a probability of probably finding an electron in that space. Again, we do not really know exactly how it's moving and where it's at, but there just is a probability. So you could kind of see the difference in sort of the color there on top, that darker area. You could kind of imagine the nucleus being there in the middle. And that is where we kind of see, really the highest probability of finding electrons, which is what we would expect. Again, there is some attraction, obviously, between the nucleus that's positively charged and the oppositely charged negative electrons, which obviously will pull the electrons close to the nucleus. And as you get further away, just like any type of magnet, right? You have a magnet, you put it next to something that's really close, it's going to grab it, right? You tip that magnet and try to grab something across the way, unless it's super strong, right? It's probably not going to move it all that much close to it. So as the electrons find themselves at further distances from the nucleus, there's not as much of a pull towards the nucleus. Thus, we see a much less of a probability of finding electrons as you sort of fan out from that positive charge of the nucleus. So this is our probability distance distribution. And when we talk about this idea of the quantum mechanical sort of model of the atom, we definitely move away from the idea of orbits to this idea of orbitals, which again, as I mentioned, really are based off of mathematical wave function sort of calculations and probability. And they are really sort of density sort of maps or probability sort of maps. And as you may be familiar with, there are different types of orbitals where we find electrons in the atom. There are s orbitals, there are p orbitals, there are d orbitals, right? And there are f orbitals. And these are all where we find electrons within the atom. So a hydrogen 1s orbital is really just a sphere. And again, kind of like what we saw on the previous slide there, it's a sphere. And again, we will see sort of a lightening of that density as you move away from the nucleus. So what we're going to do here is I'm going to skip ahead for a second, then we'll come back. And we're going to look at the orbitals here. And then we will head back the other way. So let me just find those slides. So this is on your notes. It's just a few slides down the road, I believe. Okay, let's do that. Okay, so let's talk about the different types of orbitals first before we go back to understand really based on sort of quantum mechanical model why we have, s orbitals, why we have so many of the p orbitals, or why there's 3 of these and 1 of those, and all those type of musical interludes. Yes. So let's start with the s orbital. And the s orbital, and by the way, as you might be familiar with, right, is any individual orbital, no matter where it is, what type of individual orbital it is, could hold a max of 2 electrons, right? So if this represents an orbital line, a maximum of 2 electrons, if the arrows represent the electrons, can fill an individual orbital. So s orbitals actually do start. The very first place where you see s orbitals is actually the n equals 1, or the first energy level. So there are s orbitals on every energy level: the first energy level, the second energy level, the third energy level. And as you can see here, as it goes from the first to the second to the third, and that is what those numbers represent, is the energy levels. It just gets larger to accommodate, obviously, all the electrons that are present. Nodes are the idea of what we were talking about when we talk about sort of a standing wave, like on a guitar string. When you pluck a guitar string, right? Again, it is sort of tied to it, just like the electrons are tied to the nucleus. But there are points on there where there's no amplitude, right? And that's what those nodes are. And again, that's what that is pointing to in this case. So that is our s orbital as it is moving around there. Spherical shape. There it is. Now, the next type of orbitals that we come across are p orbitals. And p orbitals actually start on the second energy level, is where they start. And there are 3 different types of p orbitals. There's the px, the py, and the pz orbital. There are different locations in 3-dimensional space. When you have a group of orbitals together on the same energy level, they are sometimes referred to as being a subshell or sublevel, depending on your book. So this would be referred to as the p subshell or the p sublevel. It is basically, there are 3 different p orbitals, which means a grand total of 2, 4, and 6 electrons if you maxed out the p subshell on any level. So if you filled up all 3 of the individual p orbitals on any level, you could put in there 6 total electrons. And you can see they sort of look like a figure 8, as we see here. And you could kind of assume that most of the, okay, I go right on that one. We'll go back the other way. Most of the electron sort of density is in this area where the nucleus is sort of there in the middle, and those are, again, probable spots of where you can find the electron present. There's the other one, again, on the Y. And then obviously here, that guy's on the other axis there.
2pz orbital is in the shape of a meteorite along the z-axis.
And the next set of orbitals that we see that really start to happen on the third energy level are the d orbitals. And there's actually 5 different d orbitals. And again, all 5 of these d orbitals together on one energy level is what is referred to again as a subshell or sublevel. And obviously, if you max out all 5 of those individual d orbitals, they each could hold 2 electrons, which obviously means you can max out at 10 electrons max for the d subshell in this case. Here's some density maps, and again, you can see kind of the darker areas of where it's a higher probability of finding an electron. You can kind of visualize again the nucleus sort of being there in the center, so you can see there's a nice congregation of probability near where the nucleus would be, as we would expect. And as you sort of fan out, obviously a little less of a probability happening in each of those cases. And that's what these guys look like.
Lies the XY plane is aligned along the X and Y axis.
The 3dxy orbital has a cloverleaf shape that lies in the xy plane and bisects the x and y axes. The 3dxz
I just like watching them spin outside.
xz plane and bisects the x and the z axis.
I like how they switch it up, like guy, girl, guy, girl.
3dyz orbital has a that lies in the y plane and bisects.
This is my favorite one. It looks like a donut. Donut. There you go. All right. So again, these are where we would theoretically and probability sort of find it. Are we going to find like a donut hanging out there in the atom? Probably not. But again, there are sort of like probability sort of maps for each of these. There's also F orbitals, and there are on the 4th energy level is where we start to see the F orbitals appear. There are 7 different F orbitals. So once again, if you took all 70 these guys together, that's going to be your subshell or sublevel. And obviously here, if we took 2 times 7 is 14 electrons max if you were to fill all 7 of those F orbitals on a particular energy level. So as we move away from Bohr's model of the atom and these idea of orbits to this quantum mechanical model of, well, we're not really sure where it's moving, how it's moving, but we do know good probability of perhaps finding an electron here. These are where we think about where electrons are sort of housed within the atom. So let us go back up a little bit and talk about really the basis for these orbitals and why we see them on certain energy levels and maybe why we don't see them on other energy levels. So what in the quantum mechanical model basically functions to help us understand what orbitals we have and everything is what is referred to as quantum numbers. And there are 4 different types of quantum numbers, which ultimately describes really things like energy levels, what orbitals you would expect to find on a particular energy level, how many, and really the orientation in 3-dimensional space, and also the spin of an electron within those orbitals, what type of spin that you would expect to have. So let's talk a little about each of these quantum numbers. So we talked a little bit first off about the first one, which is n, and that is the principal quantum number. Again, basically it talks a little bit about size, but mainly is thought of as being basically our energy levels. And n could have values of 1 through 7. And as we talked about before, our n equals 1 value is the ground state. That is what we consider the lowest in energy and closest to the nucleus. And as we saw earlier, anything above that is considered an excited state, higher in energy than the ground state. The next quantum number is L, and that's the angular momentum quantum number. That is basically the shape of the atomic orbitals, which are, again, are sometimes called subshells. the L value will really tell you, for the most part, not only the shape of it, but will tell you kind of the type of orbital you're dealing with. Is it an S? Is it a p orbital? Is it a d orbital? Based on the number that you get for that. Now, the acceptable values that you could have for L is L could have values of 0 to n minus 1. So they could all have values of whole numbers running from 0 to n minus 1. So if n was 1, I'm sorry, if n was 2, I guess we'll go with that. Why not? We'll go with that one. If n was 2, L could have values of 0 and 1, as 2 minus 1 is 1. So those are the two acceptable values you could have for L, and those will tell you something about what you would expect to see in that situation, and we'll talk about it in just a second. The next one is the magnetic quantum number, and that's m sub L. That is basically the orientation in three-dimensional space of our orbitals, like we were just watching on those wonderful animations, right? On the X, on the Y, on the Z axis in three-dimensional space. What it will also tell you is essentially how many orbitals you would expect to sort of occur. So in addition to sort of the orientation, which is really what it tells you, it will also tell you kind of like how many orbitals you got going on there. Now, when we have m sub L, for every L value that you have, you could have a specific m sub L value, and they run from minus L to 0 to positive L. So whatever L value that you have, the m sub L value will run from the negative version of that and go by whole numbers until you get to 0, and then go by whole numbers so you get to the positive version of the L value. The last quantum number here is the spin quantum number. And that is m sub S. And the spin quantum number will have a value of either plus or minus 1/2. And really what the spin quantum number tells you is kind of the spin that's associated with our electron. Electrons are moving around, they have spin, they're affected by magnetic fields, electrical fields. So the spin quantum number typically will have one of two values, either plus 1/2 or minus 1/2. And it has to do with how the electrons are technically spinning or sitting in that particular orbital. The way we sometimes can visually represent this is, like I said before, have like a little line or a box and some arrows that represent our electrons. And typically speaking, the arrow that is pointing upwards, which is usually the first arrow or electron that occupies the orbital, will have a plus 1/2 spin. And the guy that is pointing downwards has what is referred to as a negative spin, and that would be minus 1/2. So it represents the spin of those electrons within the orbital. Any questions on that? All right. So how does this relate to orbitals, electron configuration, and all that type of stuff? Let us see. Let us do it here. So if we take, let's just take our very first option that we could have, which is n minus 1. That is our ground state. Can't go any lower than that, I suppose, right? So if I have an n minus 1, which is our first energy level, the ground state energy level, I can have an L value that will run from 0 to n minus 1. So 1 minus 1 in this case is 0. Yeah. So the only acceptable L value that we would have in that situation is a value of 0. When you calculate an L value that has a value of 0, that represents our favorite orbital, which is basically the s orbital. So that is telling you what this is really telling you at this moment is on the first energy level, there can be an s orbital, basically. No other numbers are there besides 0, which means no other orbitals are going to be present on that energy level. We could have an m sub L that goes from minus L to 0 to positive L. So clearly in this case, if it's 0, the only m sub L value we could have is 0 in this case. That tells me that on the first energy level, there is only an s orbital. And there frankly is how many s orbitals? Just one. Yeah, there's only one number there, right? So there's only one s orbital present. There is not multiple orbitals in this particular subshell. And within that orbital, you can have an electron that is either pointing upwards, have positive spin, or you could have one that is negatively spin. So this is the reason these quantum numbers and these calculations are the reason why when you learned electron configuration, perhaps, they told you on the very first energy level, there is just a lonely old 1s orbital hanging out there. And this is the reason why. That is the only acceptable orbital based on quantum theory here that can be present on the first energy level. Any questions on that? So now let's see what happens when we go to the second energy level, right? We go to the second energy level. That means that n should equal 2, right? And if n equals 2, that means L could have values of 0 and 1. That's because 2 minus 1 is 1. So we could go from 0 to 1. We already know that the 0 represents the s orbital. When you have an L value of 1, it represents the p subshell or orbital. Now, for each of these L values, we can have m sub L values. So for each individual L value, you could do an m sub L value. But we already know now that on the second energy level, we still have s orbitals, like we already know, right? And this is why on the second energy level is where we start to first see p orbitals appear, because that is the only acceptable sort of level at which it can sort of appear. So if we do the m sub L value for 0, it's going to end up the same as above, right? So we will have a m sub L that's equal to 0. Now, if we do the m sub L value for the 1, it could run from negative L to 0 to positive L, which means in this case, it would run from negative 1 to 0 to positive 1. So the L value of 0 represents an s orbital. We know that we only have one s orbital, right, on any level, as we could kind of see here as well, right? The L value of 1 represents the p orbitals. And how many different p orbitals do we have based on the number of numbers that are present here? There are 3 of them, right? This number here represents the px orbital. This number here represents the py orbital, and that one represents the pz orbital in that particular case. And for each of these orbitals, they all could have an electron that is either plus or minus 1/2. That is why when we go to the second energy level, we have a 2s orbital. Because of this, we also start to see our 2p orbitals come out here, which is our 2p subshell based on the quantum numbers. Based on the n equals 2 value, there should be no other orbitals on that level except for your s's and your p orbitals. Any questions? Kind of see how they tie together so far. So let's continue on. Let's do our n equals 3 level here. On our n equals 3 level, that means the L values that you could have are which possible L values if your n is equal to 3. You could have 0, 1, and 2. Yeah, so we could have possible values of 0, 1, and 2. So we clearly already know that our 0 value is our S, our 1 is our P, and you might be able to guess, but our 2 represents the d orbitals. So this is why when we say, hey, it's not until the third energy level that we do see the d orbitals appear based on our math and quantum mechanical calculations. That is really the earliest in terms of energy levels that those orbitals can appear. Now we can do our m sub L for each of the first 2. They will come out obviously exactly the same as what we did previously. So I'm just going to do the m sub L for the second one here, the L value of 2. Again, the other ones will come out obviously exactly the same. The M sub L for our 2 here means that it can run from -2, which is the minus L value. Again, whole numbers here to -1 to 0. And then we're going to basically do the positive side of it, which would be +1 and +2. The d orbitals, right, or the d subshells have how many orbitals? How many numbers do I have here? I have 5, yeah. So each one of those represents one of the 5 d orbitals that we see. That means when we do hit, and obviously same deal, at any of those orbitals, they can have an electron that's either sort of positive or negative. So when we hit our 3rd energy level, we have our 3s, we have our 3p, and once again, that is where we see our 3d orbitals first start to appear on the 3rd energy level. Might as well finish up the 4th energy level so we don't miss out on our friend, the f orbitals. So if we go to the 4th energy level, n would equal 4. That means L could have values of 0, 1, 2, and now 3 as we do 4 minus 1. So L could be 0, 1, 2, and 3. Just like previously, that's going to be our s, that will be our p orbitals, that will be our d orbitals, and that will be now our f orbitals. So once again, just like previously, we could do an m sub L for each of those, which we kind of did right above. So I'm not going to do it again. I will do the m sub L for just the last value there of 3, but you should do them individually for each L value that you have. So if we do our m sub L for our 3, that's going to give us -3 to -2 to -1 to 0, +1, +2, and +3. F orbitals have 7 orbitals, yes, and I got 7 numbers. Each one of those numbers represents basically a f orbital in 3-dimensional space and its orientation. Each of these can have a plus or minus 1/2 in terms of the electrons in each of the orbitals that are present. So when we get to our n equals 3, 4, we have our 4s, we have our 4p, we have our 4d, and our 4f basically start to appear. Any question on the relationship there between quantum numbers and orbitals and that type of stuff? Again, here, a couple of things. We talked about that our subshell is a grouping of orbitals on a particular energy level. We also sometimes refer to as all the orbitals on an energy level as being either a level or a shell. So when we talk about the n equals 2 shell or 3 shell, that is what we're talking about. So for example, if I wanted to know the maximum number of electrons, if I in a 2p subshell, what is the number of electrons that you can put in there? You fill them up. It is 6, right? It's a 2p subshells, all 3 of those guys together, right? And each one of these could hold 2 basically, which would give you 6 electrons, right? How many electrons are max number of electrons in a n equals 3 shell or level? So the n equals 3 shell or level is everything that is on the 3rd energy level, right? So they each could hold 2, right? So 2, 4, 6, 8, 10, 12, 14, 16, and 18 electrons if you filled up everybody there. And what's the max number of electrons in a 4d orbital? In a 4d orbital? 4d orbital would be any one of these, right? Individually, which means individually they could only hold 2. Yeah. So they can only hold 2 in a 4D orbital. In a 4D subshell, how many could they hold? They could hold 10. That would be all of them together, right? In the n equals 4 shell or level, they could hold, you could count them, probably 32 is what everybody was saying, right? So you could actually, if you wanted to know how many electrons to max out a shell or level, you could actually do a quicker calculation without having to maybe draw it and count it. To figure out the max number of electrons in a shell or level, it is basically 2 times n squared, n being the principal quantum number. You actually square it first, yeah? So we just did 4, was it? 4 squared is 16, 16 times 2 is 32, yes. On the second energy level, right, 2 squared is 4, 4 times 2 is 8. Yeah, if you filled up that entire thing, so that's a good way to do it. So if I had, let's say n is equal to 5, yeah? The L values that you could have are what? 0, 1, 2, 3, and 4, right? So that is an S, that's a P, that is a D, that's an F, that is, it actually just goes alphabetical at that point after F. So you just go alphabetical after that point. Not that we ever reach any of those in any electron configuration we do. But if you want to know what it is, it just kind of goes alphabetical after that point. So G.